Hi, I'm Ian George. I'm going to talk about some joint work with Gia Lin and Norbert Luckenhaus on numerical calculations of finite key rate for general quantum key distribution protocols. So let's get started. So the motivation for this work is pretty straightforward. People are now trying to implement quantum key distribution protocols for industry use. As a quick reminder of what quantum key distribution is, it's a two-party cryptographic protocol between Alice and Bob in which they share insecure quantum channel and an authenticated classical channel, and they're trying to establish a secret key. So the problems for implementing this in real life is first that we need to handle side channels and practical issues in implementations, which may not arise in the original security proof, and also we need to be able to handle finite size behavior, which is important as in real life we only have a finite number of resources. So to summarize, the problem is that type finite key analysis normally needs certain symmetries, symmetries about the sort of signal states that we use, which induce certain symmetries in the observed data when one does parameter estimation. And this is a problem because many QKD protocols lack these symmetries, and also because, as we just discussed, when you implement these protocols in real life, sometimes you deviate from the ideal symmetries. So our solution is a numerical method that doesn't need these symmetries. It uses Renner's framework for finite size effects, and it extends the previous numerical method for asymptotic key rate without symmetries to the finite regime. So the rest of the talk can be divided into three parts. The first part we discuss Renner's finite size security framework as well as an improvement in our paper. Then we talk about the extension of the asymptotic numerical method without symmetries to the finite size regime. And finally, we look at some examples of our numerical method and discuss when it could be useful to use. So we'll start with the Renner finite size security framework. Before we move on to the results, it's important to understand the generality of these results. So the basic idea is that our numerical method can handle any device-dependent QKD protocol of the form on this slide, in which Alice sends signals to Bob, or equivalently in the entanglement-based version, which is what we'll talk about, Alice and Bob both receive their respective halves of some signals sent to Eve. Then Alice and Bob both perform their local measurements on their respective halves of the state and partition their data into public announcements, which they will announce later in the protocol, and private data, which they will use to try and establish their key. So then, after this, they perform parameter estimation, in which Alice and Bob announce all of the data about some subset of the rounds in the protocol, which allows them to determine some sort of joint frequency distribution, which determines sort of the correlation between Alice and Bob's outcomes. And then if it's sufficiently correlated, they'll continue the protocol, otherwise they'll abort. In some sense, this is the really crucial part of any sort of finite key analysis. Then, given that they pass, they perform announcements in general sifting, which allows them to throw out some portion of their data which they a priori know won't be sufficiently correlated, or any sort of other post-processing idea. Then one of the parties in this picture, it's Alice, performs the key map, which takes her raw data to some notion of a key which should be partially secure from the eavesdropper. Then they perform error correction, in which case Alice and Bob now both have this same raw key. And finally, they perform privacy amplification using two universal hash functions, which leads to both Alice and Bob having a shorter key that is sufficiently decoupled from Eve for use. So as was mentioned on the previous slide, one of the major differences in the analysis of asymptotic key rate versus finite key rate is that the parameter estimation analysis gets much more complicated in the finite regime. So in general, one could see a parameter estimation subprotocol as a CPTNI map, which takes in m of the total n states that are sent between Alice and Bob, and then maps it to just a border pass. So diagrammatically, you could see that some state rho AB is sent into their local measurement devices n times, and then they're going to use m of them to construct a frequency distribution, as discussed on the previous slide, and then they either decide continue or abort. dependent on if that frequency distribution is in some set Q of frequency distributions on which they would accept. So alternatively, one can then see that if you give a specific state rho into the CPTNI map, then what outputs is the probability of passing given that input. Another important aspect of parameter estimation for this work is the notion of coarse graining data. So one can think of fine-grained data as just the frequency distribution over the joint outcomes of Alice and Bob's local measurement devices, and then you could think of the set of frequency distributions which you would accept or abort on that set. However, alternatively, it is often useful to just think of some sufficient statistic and then coarse-grain the fine-grained data into coarse-grained data, which would be sufficient for one's uses. So for example, while in BB84 you can think of there being 16 outcomes in the fine-grained data because both Alice and Bob's measurements have 4 outcomes, the coarse-grained data would instead have, say, 2 outcomes where you just consider phase error or bit error. And so this is a coarse graining because there exists a classical probability distribution which will take the 16 fine-grained outcomes and just report the data for the phase error or bit error. We also need the notion of epsilon securely filtered states, which was first presented in Renner's thesis. The idea is that if you have some state and you're going to put it through your parameter estimation protocol, then it's epsilon securely filtered if the probability of passing on that input is less than some epsilon. So for example, if you think about the Maxwellian mixed state, and Eve's going to send the Maxwellian mixed state to Alice and Bob a series of times, but they're only going to accept on the maximally correlated statistics as if they had measured the maximally entangled state many times. You would expect that the probability of them passing on being sent the Maxwellian mixed state many times would go to 0 as the number of signals being sent increases. And so this is sort of the notion is, in principle, with finite size effects, you can't really say that there's no way that you didn't sample some specific state, but if it's sufficiently unlikely for you to have measured it and gotten the measurements that you see, then you can ignore it. So as originally presented in Renner's thesis, in the case of device-dependent QKD, there's some straightforward ways of determining the set of states which are epsilon securely filtered, which you can then throw out and just prove security on the ones that are not epsilon securely filtered. So to define this set with device-dependent QKD, you use the following information. First, you know the joint POVM of Alice and Bob, which is this gamma tilde j over some set of joint outcomes of Alice and Bob. You know that there are some statistics that you'll get when you run the parameter estimation subprotocol, and then you know your predetermined acceptance set Q. Therefore, using the law of large numbers, one can determine the set of states which would not be epsilon securely filtered given some number of tests and the acceptance set Q under the sort of joint measurement of Alice and Bob under m-fold input. So to say that more mathematically, this S mu is the set of density matrices such that under the joint measurement which describes Alice and Bob's measurement devices together, this phi p, the probability distribution under Born's rule is sufficiently close to a frequency distribution which you would accept, that is to say the one norm between the Born's rule's probability distribution and the observed in an accepted frequency distribution is less than mu, and then mu winds up depending on the number of tests you ran. It's worth noting that we're only depicting it for simplicity as being in the IID form. In Renner's thesis, he shows how to handle this for permutation invariant states, which can also be implemented in the numerics. So there's this conceptual problem in that this value mu, which determines what things are and are not in the epsilon securely filtered set, depends on the number of tests, which makes sense, but it also depends on the size of the alphabet that the joint outcomes are in. And so there are ways that you can tighten this, which tells us that this is suboptimal. So for one thing, a two-outcome POVM, instead of using the law of large numbers, you could use the Hoofding inequality, which will tighten this bound. And similarly, it implies that coarse graining can improve the bound in some cases. And so that's an issue, because that suggests that basically, since coarse graining can be viewed as throwing out information because it's data processing, it suggests Alice and Bob somehow become more secure by throwing out information. And is that true? Well, no, of course not. So before we formally state the reason we can prove this is not the case, it's sometimes perhaps easier to see it pictographically. So if you think of this blue circle as the set of density matrices, and you assume that the acceptance set Q is only a single observed frequency distribution, and then you think of two specific coarse grainings, which are represented by N1 and N2 in this picture, then you can think of the frequency distribution that would be accepted under these two coarse grainings as this FC2 and this FC1. And because of the different alphabets which they coarse grain to, or different sizes of alphabets rather, mu1 and mu2 have different sizes. And so in principle, you could look at which one has a better key rate because of the set of density matrices under their coarse graining and the size of the uncertainty, which is represented by mu. But you could also, as we show, take the intersection of these two sets, and this will get you a smaller set of density matrices, which means your key rate can only go up because you're taking a minimization over a set, and you've now made the set smaller without changing the security parameter. One thing to note, though, of course, is this is not always the case, specifically for highly symmetric data, as one might expect. One of these sets, SMU1 and SMU2, could be a proper subset of the other, but we show examples where this is not the case, which is where it helps. Right, so with the picture shown, we can now sort of see it formally. The idea is you just have some QKD protocol with some acceptable observations math calc Q, and then you consider some set of coarse grainings. So each coarse graining induces its own variational bound based on the output alphabet, and then you could consider the set of not epsilon securely filtered states under that coarse graining. So here you see you have some acceptance set Q, and then you consider the frequency distributions under that specific coarse graining and the corresponding mu bound. But then what one can show is, of course, you can take the intersection of all these SMUKs and then define this new set of states which are not epsilon securely filtered, and it will be smaller than previously by definition, and therefore you can actually increase your key rate without changing the security parameter, which no one had shown previously and actually has some uses in real-life applications, which we will soon discuss. So with the finite size security framework and our improvement addressed, we're now going to talk about the numerical method extension from the asymptotic regime to the finite size. So before we talk about the extension, it's good to understand the pre-existing asymptotic key rate algorithm that we're actually extending. So here, if we look at the Dev-Attack-Winter formula, which is this equation here, then, well, it's a rewritten version of the Dev-Attack-Winter formula. Then we see that the first term is some privacy amplification term, where we're considering minimizing over all states which satisfy the asymptotic observations, which are represented by this set S. And then the second term has to do with error correction, where the FEC is just a representation of the fact that we don't actually expect that our error correction achieves the asymptotic limit. So the second term you can determine analytically, and so the major thing from a numeric standpoint is this first term where we determine the privacy amplification. And so what Winnick-Lutkenkhaus and Coles showed was a solution to this. So the basic idea is, if you think of the set S as this light blue box, then you start with some suboptimal attack, suboptimal with respect to Eve's view, and converge to the optimal attack rho star. And then instead, because you know that you can't converge to the optimal attack, or rather, you can't prove that you achieved the optimal attack from the first step, what you instead do is you get close to rho star and you take a linearization about that point over the function, which is this von Neumann entropy, and then you take the dual and you run the dual to the boundary of the set, and this allows you to guarantee that you have a lower bound on the von Neumann entropy that you're interested in. And of course, if it were the case that rho equaled rho star, then you would have a tangent plane to this curve, and so your dual would equal the optimal solution. And that allows it to be both reliable, which is to say that it's always going to give you a lower bound on your key rate, which means you can use it in real life, and it's also tight in that in an ideal world, this algorithm will give you the right answer. So then in the finite key case, basically the idea is that we should be able to do the same sort of idea. So the key length calculation, here again I'm assuming IID attack, but we'll return to how you can do it for coherent attacks. You have some imperfections, which are to say probabilities that even though you did everything right, Eve knows the key. So these should be conceptually very small values. And then you can determine that the protocol, when it does not abort, should output a key length of some value L that's upper bounded by this value. And so the definitions, so this term H mu is again a minimization. So you can see it should be of the form of the privacy amplification again. And then the leak epsilon EC is just the error correction term again with some finite size effect. And the delta var epsilon bar is also just a finite size fluctuation effect. And so the idea is that we really only want to focus on this privacy amplification term because everything else can be determined analytically, and all that remains is to make sure that we have an algorithm that can do this privacy amplification minimization term. So again, we can do the same sort of numerical algorithm as in the asymptotic case. It's just a little more complicated now. So we still have a minimization over conditional von Neumann entropy over some states, and so we need some constraints on those states. This first set of constraints are for source replacement, so those only matter if you apply the security analysis to a prepare and measure protocol, because you need to convert it into an entanglement-based one, which you can always do, but then you need these extra constraints. Then there are the statistical fluctuations constraints, which have to do with considering the set of epsilon securely filtered states, as was discussed in the first portion. And then our way of modeling the acceptance set Q is to consider the set of frequency distributions under some coarse graining if you'd like, because in principle you can think of the acceptance set Q as always being defined on the fine-grained data so that they're within some distance of each other. This is required in the sense that we need to consider convex sets to do semi-indefinite programming. However, we note that this really isn't that restrictive of an assumption, because if you think about how QKD protocols normally work, you expect them to be rather smooth, and so normally what you have is some notion of an interval on your frequency distributions. So for example, with BB84, you might want to consider phase errors between 0 and 3%, and this assumption can perfectly handle that sort of case, which is the standard case. So we can write the whole thing as a semi-definite program, and so we can use the numerical algorithm as in the asymptotic case. So as this is beyond IID and we've discussed pretty much everything in terms of IID behavior, it's important to make it clear that our numerical solver actually can handle things outside of IID. So the first case of how people handle coherent attack is finite quantum D-Finetti theorem. So to apply this, you need to increase the size of variational distance mu, basically because instead of having IID input, you now have permutation invariant input to your parameter estimation set protocol. And then there are a couple of correction terms, and so your key rate goes down. But it's implementable by the computer, which is the important part. And then there's also this idea of the post-selection technique, which does better than the finite quantum D-Finetti theorem in terms of number of signals. And it says that if you have an epsilon secure protocol on collective attack, then it will be polynomial secure on epsilon secure on the coherent attack. And so basically the idea is that you calculate the collective attack and then you divide all the security parameters by this polynomial value to determine the coherent attack. There's some extra difficulties with this that are minor, but one could always look at Norman Beaudry's thesis where he explains how to handle these. So to take away, the solver is for both coherent and collective attack analysis. There is one caveat, which is, as I mentioned in the previous slide, sometimes one wants to consider prepare and measure protocols, in which case one needs to handle source replacement. And actually, there does not exist a security proof which handles source replacement in a natural fashion. So one can always do finite quantum D-Finity theorem and come up with a sort of a hypothetical protocol that's related to the original one, where you let the extra restraints of the source replacement be handled. And so one can still prove security for general protocols using that. However, the post-selection technique requires that the attack be epsilon secure for all D-Finity states, which are convex combinations of IID states. And while that holds for entanglement-based protocols, we know that, in fact, if you need to take a prepare and measure protocol and move it into the entanglement-based view, this is no longer the case. That is to say that there are IID attacks which you're not secure against because you need to fix the marginal of Alice's space in the source replacement regime. So post-selection technique actually does not hold for source replacement coherent attack analysis. And the finite quantum D-Finity theorem does, but it will continually make the number of signals necessary to get a good key rate worse than it already did just from the entanglement-based version. So this is an open problem. So just as a quick example of applying coherent analysis of BB84, where you view we're considering the entanglement-based BB84. So here's the IID collective attack. And then this is the quantum D-Finity, where these jagged lines just have to do with the fact that I did like a discrete optimization over the protocol. One could, of course, smooth this out. And then lastly, one can look at the post-selection technique, which one can see does significantly better than the quantum D-Finity theorem in some sense, because it is more stringent on the requirements that the protocol has to satisfy. So that gives a intuition. But so now all of my examples will just be for the IID collective attack to get the concept. So we now move on to the examples of the numerical method. So the first thing to do if one has a new numerical result is to make sure that it can at least do as well as the pre-existing analytic results. So here we're considering the Scarani-Renner paper for BB84, where we see the dots are our numerics and the lines are the analytic results, and you can see that they overlap each other, which means that it's tight in this case because it's a nice simple protocol. We now want to look at something where the discussion about coarse graining and using multiple coarse grainings can actually help our key rate. So one place to think about this would be reference frame misaligned BB84. So in BB84, Alice's signals are these 4 dots on the block sphere, and you could imagine that she's going to send these to Bob, and she sends them through a channel that rotates them. And so from Bob's point of view, he now gets these 4 dots on the block sphere, but they aren't the proper signal states. And so it's as if Alice sent Bob a rotated reference frame. And so the idea is with parameter estimation, he should be able to like unrotate the reference frame, and so the key rate shouldn't be affected by this. But if you didn't use sufficient parameter estimation, you could not do this. And so the basic idea is that when people normally look at BB84, they coarse grain to phase error. And when you coarse grain to phase error, you don't actually have sufficient statistics to undo this rotation. So that's what we're going to look at numerically. So another way of saying what I just said is that if you think about it, when she sends the simple model and there's no rotation, then coarse graining is fine because these pink boxes are the phase error and bit error respectively, and everything's nice and symmetric. And so the key rate's really determined by the phase error. But if you apply this rotation, then you can see that the bit error and phase error have gone up. But because of this rotation, there's this asymmetry now in the sifting blocks. And so if you kept this fine-grained data, you'd actually be able to undo the rotation. And so you could get your key rate back to the optimal one, because you're actually sort of overcounting what came from phase error versus what came from a unitary rotation by Eve. And Eve can't gain anything from the unitary rotation. So just basically in the asymptotic, you see under this rotation, the phase error is lower than the full statistics, and the reason we know this to be the case, or we would expect this to be the case, is because it's just said the unitary can undo the rotation, at least in the asymptotic limit, and so at some point you're going to get some benefit from undoing that rotation. However, because of the way the security for finite size effects works, it scales as a function of the number of outcomes, and so in the small signal limit, phase error is doing better because it only has 2 outcomes under the coarse graining, whereas fine-grained statistics has 16 outcomes. So then the idea is that because we have this numerical solver that can handle both of these things at the same time, and we have a theorem saying that we can keep the security parameter the same and do this multiple coarse graining, we actually get this key rate which is better than both of them in every case, because it has the advantage of forcing it to satisfy the phase error observations and also forcing it to undo the rotation because of the fine-grained statistics. And so this is the major power of our results. Beyond the basic BB84 that we just discussed, one of the major advantages of our numerics is it can handle any QKD protocol which can be represented in finite dimensions. So here we just think of a very basic example of MDI QKD between Alice and Bob and Charlie. And the reason we can handle MDI QKD is because there's nothing in the way parameter estimation is defined that it has to be a bipartite joint distribution that we can consider tripartite or whatnot. So we're able to implement this numerically. We also often want to consider optical implementations of QKD protocols for practicality reasons. However, these have the issue that they generally cannot be represented in finite dimensions because optics is represented in infinite dimensions. However, in some cases there exists a squashing model which allows us to represent without any sort of looseness in the security the optical implementation in finite size. And so here, as an example, we consider the discrete phase randomized BB84, in which case the basic idea is that in principle you could just send 4 coherent states, which would be like BB84 or the low Preskel protocol, but you could also add a global phase to the state, which is hidden from Eve and also from Bob, in which case you could do that over and over. And so, for example, here we're just considering 2 discrete phases, either no discrete phase or this 1 rotation. So here we see the discrete phase randomized BB84 for 20 kilometers, and you can see the sort of number of signals that it takes to get a positive key rate. This is without any sort of coarse graining, so it's possible there would be less signals necessary. And then also we see that if you go to 100 kilometers and so your loss goes down, then basically the number of signals to get a positive key rate goes up. But of course this makes sense because more and more of your signals are just going to tell you whether or not there was a vacuum received, and so you need enough signals to properly determine one's decoupling from Eve, which has to do with the outcomes which relate to key generation. In many finite size works, they assume that the acceptance set Q is actually a single frequency distribution, and this normally results from an assumption about the sort of symmetric observations that their protocol will achieve. So for example, if you think of BB84, since you know that the phase error is a sufficient statistic if you have symmetric data, then it is sufficient to just consider the highest phase error that you would ever accept And so implicitly what one has done is done the analysis for a single frequency distribution f, which will determine a sufficient key rate for all frequency distributions that have a phase error less than some threshold. However, this is not in general going to be the case, as there are imperfections in devices, and so it would be useful to have a numerical solver that can handle the practical acceptance set Q, which is one of the major results of our work, as we can in fact consider that. So for example, if you consider the symmetric BB84 here, where you just accept on some set of phase error frequency distributions, then you can see that the phase statistics, that is just using the phase statistics, are these dots, but using both the phase and the fine-grained statistics doesn't do anything better because the data is sufficiently symmetric, and so you have a sufficient statistic. However, in the case where you have some rotation for some reason, it's actually very important to be able to consider some set of phase and fine-grained statistics. So for here, the set Q2 is actually some set of observations that are rotated, because that's how your protocol is going to behave for some reason that perhaps is out of your control. And so here, the ability to consider arbitrary acceptance set Q and also be able to do multiple coarse grainings can sufficiently increase one's key rate. So to summarize, we improved the analysis of the parameter estimation subprotocol by showing how to consider multiple coarse grainings, which resolved the conceptual issue in the notion of finite size effects. We constructed a general numerical solver for determining the finite key rate of QKD protocols represented in finite dimensional Hilbert spaces, where we have a generality in types of protocols. That is, we can consider qubit protocols, qubit MDI protocols, optical implementations that admit squashing models, and then also we have generality and practicality because we're able to consider an acceptance set Q so long as it's convex. And then lastly, we considered when our improved parameter estimation, which is to say the first result, can be advantageous, which is specifically for asymmetric observations, which is going to be useful for implementation errors, and also we hope could be used for investigating side channels in the finite regime in the future. So thank you.